So we continue our study of electrodynamics, and as promised, today I would like to explain to you how we come to the Hamiltonian formulation of the electrodynamics, so how to write down the Hamiltonian, the corresponding Poisson structure, and then we will quantize the corresponding Hamiltonian theory. And the starting point, as usual, is the Lagrangian for electromagnetic field, which is L, given by -1/4 integral dx, three-dimensional integral, and then f mu. So electromagnetic tensor. And in addition, there is a term which describes interaction of electromagnetic field, A mu, with a conserved current, J mu, representing the material particles, like, for instance, electrons. Now, to simplify our considerations, well, at first step, I will assume that the current J mu is actually absent, is zero. So we consider free electromagnetic field. Free means without sources. And source is this current, which we consider now to be absent. The first step, which I will do towards writing the Hamiltonian version of electrodynamics, the first step, I will present the corresponding Lagrangian in the so-called first-order formalism. It's called first-order formalism. Or another word for this is phase space Lagrangian. So what is this? First of all, we compute the canonical momentum conjugate to the field A mu. So as you know, canonical momentum P mu on X, the standard definition is derivative, no variational derivative in this case, of the Lagrangian with respect to velocity of our field. So A mu, as we already discussed, is considered as a coordinate. So A mu is a coordinate. And therefore, velocity corresponding to this coordinate will be A mu dot. No, here I use A mu with an upper index. So let's write A mu with an upper index. A mu dot would be the corresponding velocity. And as usual in the Hamiltonian formalism, we need first to find the canonical momentum. So canonical momentum is dl over dA dot mu. And we see that in order to compute this variational derivative, we will have integral d, say, y, integral over dy, f rho nu, let's write it like this, depending on y. And here, variational derivative of d rho, say, a nu, depending on y, over d, let's write time derivative as dt of a mu on y. Oh, sorry, or a mu on x. So because we consider p mu depending on x, so this would be the variation. So you see, f mu, just to remind, is d mu a nu minus d nu a mu. And since f mu comes quadratic, when we do variation, we first vary f mu squared, so it gives the coefficient 2. And then variation goes to f mu, and coefficient -1/4 becomes -1/2. But then f mu itself contains two terms, d mu a nu minus d nu a mu. But since f mu, which remains, is antisymmetric in indices mu and nu, we can suppress one of the terms, when we do the variation, and just reduce the coefficient -1/2 to 1. That's why this -1/4 turns into 1. And then this is nothing else as you see here, there will be delta function appearing, delta function of y minus x. And so you can perform an integration, and rho must become t. And I remind that rho, sorry, that say x0, which is the first component, is ct. So there will be a factor of c appearing. And as a result, what you will have here is -1/c f0 mu depending on x. Or if I put the index 0 down, I will have -1/c. This is Minkowski metric, so -1/c f0 mu depending on x. So the outcome is the following expression for the canonical momentum: 0 mu depending on x. Any questions here? Is it clear how I have computed the canonical momentum?
Yes.
Yes.
What metric signature do we have?
Metric
plus,
signature,
minus, or
we have plus, 1, minus, minus. The others are minuses. So the time component, which is this 0, corresponds to +1. So we can just put it down without change the sign of the sign. This is our Minkowski metric. Eta mu. That is the metric which I'm using here. Okay. Okay, so then what do you see from this formula? From this formula, you see that if you consider, if you restrict this index mu to be 0, so P0 is -1/c f0, 0. But the electromagnetic tensor is antisymmetric with respect to indices mu and nu. Well, you see it from this formula. And therefore, a 0, 0 component is just 0. So P0 appears to be 0. And this is what is called in the Dirac language the primary constraint. Primary constraint. So in fact, this means that not all components of P mu are independent. We derive the canonical momentum using the standard procedure, using the standard prescription of how to compute it. But then we see that actually component P0 appears to be 0 automatically. It's just a property of electromagnetic tensor to be skew symmetric. And such constraints, which just follow from the definition of the canonical momentum without using anything else, without using equations of motion, just from definition of the canonical momentum, such constraints, according to Dirac classification, are called primary. And the problem here is that once you realized that P0 is equal to 0, this means that you are not able to express all the velocities via canonical momenta, because you have 4 velocities, a mu dot, index mu is running 0, 1, 2, 3. So you have 4 components of velocity, but you have instead only 3 components of momentum, because P0 is equal to 0. So this means that you cannot replace velocities, you cannot express velocities via canonical momentum, which is needed to pass to the standard Hamiltonian formalism. And according to Dirac, this means that you are dealing with a singular dynamical system. Singular dynamical system. Singular dynamical system according to the classification of Dirac. So you cannot pass to the Hamiltonian formalism in the standard way. Again, for the simple reason that you are not able to express all velocities via canonical momentum. As to the other components of the canonical momentum, they coincide up to an overall factor -1/c with the electric field. That you can see very explicitly from the following consideration. So you take pi on x. What is this? This is -1/c f0i depending on x. This is -1/c d0ai minus dia0. And if you look at the electromagnetic tensor, how it's constructed via electric and magnetic fields, you will see that what is this? This expression is this -1/c, simply ei, where ei is an electric field. So canonical momenta corresponding to spatial index I running 1, 2, 3 is up to this -1/c coefficient simply an electric field. So this means that ai is a coordinate, and essentially ei, let's write ei, is its canonical momentum. So canonical momentum is an electric field with respect to the coordinates represented by electromagnetic potential. Okay, so this means, in fact, that we can solve for ai dot, that we can do via pi. So ai dot is this term here. So we put di a0 to the left-hand side, and then the expression will be, so I multiply by c, and then I will get ai dot to be given by ei plus di a0. So I'm comparing this and this. So minus goes away, and I express this d0 ai via electric field and this extra term di0. So this is how ai dot looks like via electric field and the derivative, spatial derivative of potential A0, electromagnetic potential A0. Now, first order formalism is needed in order to develop the Hamiltonian formalism for this singular dynamical system. We still aim to construct the Hamiltonian formulation, but now we have to be careful because we understand that this is an unusual situation where P0 is equal to 0. Now, the idea of the first order formalism, or in other words, phase space Lagrangian, consists in representing the Lagrangian in this specific form. So I'd like to rewrite Lagrangian in the following way. So dx, pi on x, so momentum, ai dot on x, minus whatever makes a difference between this term and the Lagrangian. And this difference I call rest. So the remaining terms which makes a difference between the Lagrangian and this term here. Now, why this term does appear? What is importance of this term? Why I insist that I would like to have it on the right-hand side? The point is that this term describes actually the symplectic structure of our dynamical system, of the model. Symplectic structure, and the other way, it's a mathematical term I'm using here. The other way to say is that this term is responsible for the Poisson bracket, Poisson structure, or simply Poisson bracket between our fields, between PI's canonical momenta conjugate to the variable AI. Now, this I can clarify why it is so, but let me for the moment just to proceed with finding out what is the rest. So let's try to find the rest. So we understand then that the rest is given by integral dx pi on x ai dot on x minus minus Lagrangian, right? And now, sorry, now we substitute dx pi on x ai dot on x plus our Lagrangian is 1 over 4 integral dx, and then I will write it in the following way. So I split time component of f, which is minus twice f0i, and the components which contain only spatial directions, fij. This is the same as what I'm writing here is the same as f mu.
Professor.
Yeah, sure.
Here, are you finding the Hamiltonian?
Yes, in a way, I'm trying to find the Hamiltonian. Yes, but this term which I'm writing here, like pi ai dot, guarantees me that there will be canonical Poisson bracket between pi and ai. Once I've written the action in such Lagrangian in such a form, then this term here guarantees that pi and ai are canonical variables conjugate with respect to the Poisson bracket. So Poisson bracket between pi, between momentum and the coordinate, will be standard canonical Poisson bracket. That's the reason why I'm writing this expression. Now, this expression is a bit unusual in a way that this Lagrangian depends on coordinates, on AI. It depends on momentum, and it also depends on velocity. It also involves velocity. So it's kind of hybrid formulation. It contains Hamiltonian variables, which are coordinates and momenta, but it also contains a Lagrangian variable, which is a velocity. And the velocity is only in this term. It present only in this term. The rest I would like to rewrite only via coordinates and momenta. So this will be a function. This rest will be functional of pi and ai. That is an idea behind it. And indeed, this rest will contain the Hamiltonian, as you will see in a moment. Okay, so we continue a bit. And we see that this is integral dx. Now I substitute for ai dot. I know that this is essentially ei. And then there is also this c will be cancelled. So c from ai dot and c from pi coming from pi will be cancelled. And ai dot I replaced by this expression here. It will give me ei plus ti a0, right? So this will be my kinetic term or whatever term responsible for the
I'm
Poisson
sorry.
bracket.
Where did the minus 1 over c come to?
Minus 1 over c is here. It sits in pi. Minus 1 over c sits in pi, right? And
but I mean, it's you replaced pi with ei, but it's actually minus 1 over c ei.
Yes, but there is also ai dot, which I'm replacing by this expression here, and that cancels this c, because c1 over c cancels with c.
Yeah, but there is also the minus sign.
Minus sign somehow also goes away. That's because I raised the index I. I think what I have done here, I'm writing ai dot with index I up. and here I write an index dot a dot with which is down. So when I raise it up, because of the Minkowski metric has a signature +1, -1, -1, -1. So special index I is raised or lowered with a minus sign, you see, and that's the reason. So this was with low index, and this is with upper index. So when I raise an index, there will appear minus sign here. So if I allow myself to raise the index here, then the result will be AI with upper index is minus C. And this minus C, let me do it in red. Okay, let me do it in red just to show you that this is -1 over C. Will cancel with this minus C. Okay, so then these two canceled, and this is what I'm writing here. Agree?
Oh, yes, seems fine.
Okay, and then what we have here is, let me just write it as follows. So +1 over 4. Okay, I will write it once again. So rest, which we are finding, is integral dx EI plus DIA0 +1 over 4. And then this term.
Am I the only one who doesn't see the whiteboard?
Yeah. Do you see whiteboard?
Yes, it is visible.
You see the whiteboard?
Yes.
Yes.
Now I also see the whiteboard.
Okay, so probably there is some delay in delivering. Okay, so 1 over 4 dx. And then I substitute F0I via electric field. And this is -2 electric field squared. So EI, sum over I write this EI squared plus Fij. So this is how this rest looks like. And let me remind that H was introduced as a curl of, it's a curl of A, like this. And in terms of the electromagnetic tensor, as a component of electromagnetic tensor, the magnetic field can be written in the following way, can be detected from electromagnetic tensor by taking a pairing of electromagnetic tensor with a antisymmetric tensor epsilon ijk. So sum over j and k. So this is a way to extract magnetic field from electromagnetic tensor. Well, you remember probably this expression I gave you for F mu. So F mu was 0 electric field Ex, Ey, Ez, or E1, E2, E3, minus Ex, minus Ey, minus Ez. And here you have 0 minus Hz, Hy, 0 Hx. Here there would be Hz by skew symmetry, and here minus Hy, and here simply must be 0. Hx under this. So skew symmetric tensor. Like this. And if you want to detect these components of magnetic field out of this F mu, you first restrict yourself to Fij. So this is this block here. It does not involve 0 component. And this is this Fjk. And then if you multiply this matrix by epsilon jk, then you can check that you exactly detect the component of the magnetic field out of electromagnetic tensor. Now, also we know that epsilon satisfies the following property. So if you say take a summation of the first index of two such tensors, let's write the second one, say as I m n, and you are summing over index I, then the result will be the following: delta j m delta k n minus delta j n delta k m.
I'm sorry. Is it really true that HZ and HY both have the minus sign before them?
No, sorry, no.
FQ?
Here probably there should be plus. In one case, sorry, yes, there should be plus, of course. I think here, this is a plus here, not minus. Plus, tensor is skew-symmetric, so therefore, in one case it's plus hy, and in another case it's minus hy. Okay. Yes. So we have this formula, which is nice and important formula for summation of epsilon tensor with respect to one index of it. But this formula allows us to compute hi squared. So if I take hi, which I write as hi squared, this means that I will have 1 over 4. I'm using now this formula and substitute it here. So it will be 1 over 4 epsilon I jk epsilon I mn f jk f mn, right? So square, square of h. Then I use this formula for epsilons, yes, for sum of two epsilons. And this gives me 1 over 4 delta jm delta kn minus delta jn delta km multiplied with fjk fmn. Now you see what happens if you replace, say, index k, say, with n. You will get 1 over 4. So from the first term, f jn, f and m you replace by j, so you will get jn minus f k we replace by, say, or maybe we can just leave it fjk, and m we replaced by k, and n we replaced by j. But since tensor is skew-symmetric, we can write this fkj as fjk with a plus sign. So allow me to write simply plus here, and here to change the index for jk. And we are summing over j over n in the first term, and over j and over k in the second term. So these are dummy indices. So in fact, these two terms are equal. And you can write, therefore, the answer by replacing dummy indices with new indices I and j. So this will be 1 over 2, because these two terms are equal, fij, fij. This means, in fact, that we can replace in our term here this fij, fij with hi squared, hi squared. The only thing which I have to check is the following. I don't quite, minus 2ei squared, fij, fij. And the only thing which I don't quite get is I'm missing minus sign. missing minus sign. So in any case, let me write. So the rest should come out in the following way. So the rest is
I'm sorry, where exactly do you miss the minus sign?
yeah, I will write an expression which I have to get because I think I'm still missing minus sign. Let me see. No, I'm not missing minus sign. I guess I understand what's happened. Yes, I understand. So you see, okay, let's continue. So the first term dx also contains ei squared. And so there is ei squared here, right? This is ei, so ei squared plus ei di a0. And I can write all terms together now. So from this second, I will get minus 1/2 ei squared. And from Fij, I will get 2hi squared. And 1/4 with 2 gives me plus 1/2 hi squared. Right? This is what I will get. And therefore, this ai squared together with this guy here will give me 1/2 ei squared. So the result will be integral dx 1/2 ei squared plus hi squared, correct? Plus integral ei di a0. And this term I will integrate by parts and throw away the total derivative, total special derivative. So this gives me a0 multiplied with di ei. So this is how the rest looks like. And if I return back the rest into the original Lagrangian, so let me remind that original Lagrangian was written in the form pi dot minus rest. So then means L is given by the following expression. Minus 1/c, if I write it via ai dot, integral dx ai dot. So this is canonical momentum minus 1/c ei. This is pi, multiply with ai dot. And then minus rest. And rest we just computed. So it's minus 1/2 integral dx ei squared plus hi squared plus integral dx a0 di ei. So we have achieved our goal. So we written the phase space Lagrangian. So once again, the meaning of the terms entering this Lagrangian is the following. So this gives us symplectic structure, the Poisson bracket between ei and ai dot. This term here has the meaning of the Hamiltonian of electromagnetic field. And this term is a new kind of term where a0 plays the role of Lagrangian multiplier to the constraint diai. So this term is, I will call constraint. So what is interesting to point out here is that this term a0 appears without time derivative on it. There is no time derivative of a0. And this is clear from the original Lagrangian. So original Lagrangian was minus 1/4 integral dx f mu, right? That was our original Lagrangian, f mu. And
I'm sorry, by symplectic structure, do you mean the symplectic potential?
I mean that this term is responsible for the form of the Poisson bracket, for the canonical structure. I will write in a moment what it means. So if you look at F mu, so F mu is d mu a nu minus d nu a mu. You see that this electromagnetic tensor never contains a zero dot, because a zero dot would mean that you have a term d0 a0. No, up to 1 over c, this is d0 a0. But d0 a0 cannot appear because indices mu and nu cannot coincide. If they coincide, then the corresponding component of the electromagnetic tensor is 0. You see on the diagonal, you have zeros of electromagnetic tensor because of skew symmetry. So such term never appears in the action, in the Lagrangian, and only potential A0 itself, because of integration by paths, appear by paths of special derivatives. These terms di A0 can appear, but if you integrate by paths, then A0 stands alone, and it never contains a time derivative. So this is another peculiarity of electromagnetism. A0 appears without time derivative on it, and so in fact it plays the role of the Lagrangian multiplier. If we consider equation of motion for a field A0, we get immediately di ei, and this must be equal to 0. And what is di ei? This is divergence of E. If I write it in terms of this symbol divergence, where you see it's divergence, it's three-dimensional divergence, di ei. Divergence of E is equal to 0. And as you know, this is one of the Maxwell equations, right? Divergence of E is equal to 0 in the absence of sources. This is a Maxwell equation from the second pair of Maxwell equations. And the other name for this constraint, for this equation, is Gauss Law. Gauss Law. I think I mentioned this already in the last lecture. So we see that Gauss Law, this constraint, appears to be a constraint which comes into the this phase space Lagrangian with a multiplier whose role is played by the potential A0, by the scalar potential. So scalar potential, in a way, is dual to this Gauss Law constraint.
Excuse me, Professor.
Yeah.
We also say that on the constrained surface, del I ei should be 0, right?
Yeah, so constraint, you mean constraint means that now the dynamics of this theory happens on the surface divergence of E is equal to 0.
Yes. Now, if we have a source term, then del I ei is not 0, right?
Yes, also yes, and it will not be 0, but we will see what happens. I will add sources a little bit later. Yes, I will add sources. I will show you how this is modified.
Okay.
Now look at the Hamiltonian. This is EI squared plus HI squared. So what is this? You probably, if you had lectures on electrodynamics before, I don't know if you had them. If somebody told you already electrodynamics before.
Not in the master's program, but I think that most of people have.
Yeah, then you probably, if you look at this expression carefully, you realize that what is written down here is what is called energy of electromagnetic field, right? Sum of squares of electric and magnetic field. So that's exactly the energy stored by electromagnetic field, exactly this expression. 1 over 2 integral dx EI squared plus HI squared. This is a component of the stress energy tensor of electromagnetic field, component T00, which is responsible for the energy. No, and we see it appears in this when it just coincides, you see, with a Hamiltonian, which we get by means of this phase space approach, Lagrangian approach. Now,
I'm sorry. Could you please remind why must the derivative of Lagrangian with respect to A0 be equal to 0?
Because A0 is a variable, is a dynamical variable, which you have in your Lagrangian. So it's a field. It enters your Lagrangian. And if you want to derive equations of motion, then you have to vary Lagrangian with respect to all the fields. So typically, you would expect that your expression is d over dt, d Lagrangian over dA0 dot minus d Lagrangian over dA0. So it's an Euler-Lagrange equation. So what I'm writing down here is an Euler-Lagrange equation. So Euler-Lagrange equation for A0, right? Equals to 0. That's standard Euler-Lagrange equation. But since there is no dependence on A0 dot, this term is absent, and you are left with L over dA0 equals to 0. So A0 comes algebraically without time derivative. And so this is Lagrangian multiplier in our standard language of mathematics, Lagrangian multiplier, and therefore it generates for us this constraint. Gauss law, which is Gauss law on the one hand side, on the other hand, we know that this is one of the Maxwell equations without sources. Very good. So the Hamiltonian, therefore, H, I will denote it by H straight and bold, not to confuse it with magnetic field. So H is 1 over 2 integral dx EI squared plus HI squared. So magnetic field plus contribution of magnetic field plus contribution of electric field. This is Hamiltonian. The second thing is this, I'm telling you about this symplectic structure or Poisson bracket. So this term here means that Poisson bracket between electric field, which is a momentum essentially, and the coordinate, which is this AG on another point, say y, equal time Poisson bracket between momentum and coordinate is canonical. This means that it's given by minus c delta ij delta function x minus y. And this expression, in fact, is a consequence of this form of the Lagrangian, of this symplectic structure term, which we have here. This means that the bracket between EI's is 0. So canonical bracket, if you want the whole set of brackets, so EI with EJ on Y is 0. And the same is also with potential. AJ on X, AJ on X, AJ on Y equal time is also equal to 0. AJ, let's put here, say I, and here will be J, is equal to 0. So the structure is canonical. That's what we call canonical Poisson bracket. Momentum with the coordinate gives delta function and delta Kronecker, while components of momenta commute between themselves and the coordinates commute between themselves with respect to the Poisson bracket. So this
is only for this, right? If for example, if our field was interacting, then the Poisson bracket between AI and AJ would be non-zero.
No, it still will be 0. it still will be 0. I'll show you how it is modified for the interacting theory, but it still will be 0. Now you can check that this bracket which I'm writing is compatible with all the scalings. So to remind, electromagnetic potential has a physical dimension equal to, let's write A mu, or simply A without index mu. Every component has a dimension square root of h bar c divided by length. That is the physical dimension of electromagnetic potential, h bar c by length. But h bar c, square root of h bar c, is the same as the dimension of electric charge. So this is electric charge, if you wish, divided by length. That's the physical dimension of field A. The dimension of electric field, so electric field is a derivative, as we know, it's a derivative of A. So therefore electric field itself has a dimension square root of h bar c divided by L squared, because it's a derivative of A after all. Now, if you substitute these dimensions to the left-hand side, you will get h bar c divided by L cubed, h bar c divided by L cubed. And the same you see on the right-hand side. So C you have, and delta function has dimension 1 over L cubed. It's three-dimensional delta function, so it's 1 over L cubed. And h bar, this is a standard offset which you have between the Poisson bracket and its right-hand side. That it should be the case, because Poisson bracket is a differential operation which involves differentiation over dp, say function df over dp. Let's write it df over dp, dh over dx minus dh over dp, df over dx. And you see that p and x together, they have a dimension of angular momentum, right? P multiplied by length is the dimension of angular momentum, but the dimension of angular momentum is the same as the dimension of the Planck constant. So because of this differential operation, this h bar on the left-hand side will be cancelled. It will be cancelled, and then you get the agreement of the dimensions between left and the right-hand side. This is just to check that this Poisson bracket has a meaning, that this, for instance, speed of light appears on purpose to the right-hand side.
I'm sorry, but is that you call the symplectic structure the symplectic potential? So is it there? Like in classical mechanics, we have the one form PDQ.
It's PDQ, yes. It's PDQ.
And on some other lectures, for example, on Sharygin's lecture, we introduced symplectic potential, which is, as far as I can understand, the generalization of this PDQ one form.
If you wish, what I'm writing here is PDQ. So PDQ, if you parameterize Q with the time, then you can write it as PDQ over dt. And this is exactly what you have, P multiplied by Q dot multiplied by dt, right? And this is exactly what is standing here. E is P, minus 1 over C, E is P, no, and Q dot is A dot. Is it, if you call this term a symplectic potential, then this is what it is. Potential, maybe, I don't know why you call it in this way, maybe because
the exterior derivative of this is the symplectic.
Yes, that's what I'm saying here, exactly. So this is dp dq. Yeah, so this probably is what you meant, right?
Yes.
Derivative or differential of PdQ gives the symplectic form. Here, in this case, you can call PdQ symplectic potential. Then this is a symplectic potential in your terms, and this is symplectic potential indeed. I call it symplectic structure, but okay, that's in fact potential responsible for the standard form dpdq, and the standard form dpdq, inverting it gives the canonical Poisson bracket, exactly the one which I'm writing here. So inverting this dpdq gives a Poisson bracket, the standard Poisson bracket, which tells you that bracket between p and q, is 1, pp is 0, is 0, and QQ is 0. That is canonical Poisson bracket. No, and now it's implemented in a little bit more complicated setting, in the setting of fields, where we have fields depending, parameterized by the space-time, by the space point x. Okay, that answers your question probably, right?
Yes.
Okay, very good. So what you can also do, you can load down this index J with A and also write this bracket in the form EI. Stop writing. EI AJ on X. I don't know what happens to my pen. It's not writing anymore. Strange. AJ on Y is equal to C delta IJ delta X minus Y. Like this. Well, since you have the Hamiltonian and the Poisson structure, you can now derive equations of motion in the Hamiltonian. Well, you can derive simply Hamilton's equations. You can write down the Hamilton's equations. And what are the Hamilton's equations? These are equations which tells you that dH, say three-dimensional vector over dt, must be obtained as a result of the computing of the Poisson bracket of our Hamiltonian H with a magnetic field. With the magnetic field H, like this. And if you do this computation, so you have a bracket, so you have the Hamiltonian, you substitute the Hamiltonian into this bracket, and then the result of this will be minus C curl of E. That is what follows by straightforward computation of the Poisson bracket. Please check me. And dE over dt. dE dE over dt will be the Poisson bracket of the Hamiltonian with E. Yeah. Just a second, I have to change probably a pen because mine is not writing really. Just a moment, I'm changing the pen. Let's see if it will become better. Which gives C multiplied with H. So what is this here? Do you recognize this right-hand side? So what is written down here? dH over dt minus C curl of E, and dE over dt is C curl of H. Do you recognize what is this?
The second pair, Maxwell equation.
Exactly, these are Maxwell equations. So we reproduce, in fact, Maxwell equations. The first one is from the first pair, the second one is from the second pair. On the top of this, the dynamics must happen on the constrained surface. Divergence of E is equal to 0. So that's another Maxwell equation. That's another Maxwell equation. Divergence of E is equal to 0. And there is one more equation which tells that H is curl of A, but this is implied. This is implied by the construction. So this is a relation between magnetic field and vector potential. That is something which is built from the very beginning in this formalism. H is not independent field. This is just understood as a curl of A. So in this way, you reproduce all Maxwell equations. So you have all Maxwell equations, and this main equation for dynamics of H dot and E dot, they are obtained as really Hamilton's equations, where the role of the Hamiltonian is played by the energy of electromagnetic field, and Gauss law appears to be a constraint. Now, this constraint, so divergence of E is equal to 0, is actually preserved in time by the Hamiltonian. So you may compute, say, if it denotes this constraint C, call it C on X, and identify it with a divergence of E. Divergence of E. So then you can see that dC over dt is actually equal to, well, according to the Hamiltonian dynamics, that should be a Poisson bracket of H with C. Is C on X. And if you substitute here, indeed, this divergence, dI, then you find out that the result of this will be 0. What happened? Also, what you can see from this construction is that the Poisson bracket of C on X with C on Y. So constraint computed at different points, Poisson bracket of this quantities is actually equals to 0. And according to the Dirac terminology, this means that C on X represents a constraint of the first class. So constraints of the first class, these are constraints whose Poisson bracket vanishes on the constrained surface. So if you compute the bracket, say constraint, one constraint with another one, on a particular constraint with itself at different space-time points, we find that it's actually vanishes everywhere, not even on the constrained surface. And so in this case, we can say that C on X belongs to the first constraints of the first class. So in other words, we have introduced the division of the constraints into primary constraints, and there is also secondary constraints, but this is I have not discussed, and the secondary constraints did not appear in this construction. So primary constraints we have seen, and the other division is a division on the constraints of the first and the second class. And constraints of the first class are those for which the Poisson bracket of the constraints vanishes on the constraint surface. And so we see that this is indeed the case for us here, for this Gauss law, and therefore Gauss law is a constraint of the first class. Now, of course, we have seen that our original Lagrangian, which we write as -1/4 integral f mu, was invariant with respect to gauge transformations. And it is clear that if we rewrite our Lagrangian in the other form, say, as we do here, we rewrite it in the phase space form, this gauge symmetry, of course, is maintained. So it does not disappear. It is there. Well, you can see it from the following, easily see it from the following argument. So the gauge transformations have the following form. Say AI transforms, if I write it explicitly, I write it like this: AI goes to AI plus di chi, where chi is an arbitrary function of space and time variables, and A0 transforms, which is a scalar potential phi, transforms as A0 minus 1/c chi dot. So this is D0 chi. This is the same as to say A0 minus D0 chi. These are gauge transformations of the vector potential and the scalar potential. So in four-dimensional notations, you can write this as, say, A mu goes to A mu minus d mu chi. Then under these transformations, our gauge fixed Lagrangian. So let's have a look at gauge fixed Lagrangian again. Where is it? Here it is. So we know that electric and magnetic fields do not change under gauge transformations. So Hamiltonian is invariant under gauge transformations. It does not change because it's just the sum of squares of electric and magnetic field. Here, EI is also invariant. AI dot will be changed. And here, DI, when this term is also invariant, so it will not be changed. So only potential A0 will be changed. So AI dot and A0, these are the only terms which will undergo change under gauge transformation. And so variation of the Lagrangian under gauge transformation then takes the following form: -1/c integral dx EI. So this is from symplectic structure. And then AI dot will be changed to DI chi dot. And the term from the containing Lagrangian multiplier will be changed as -1/c integral dx. And now A0 will be changed to chi dot di EI. So this is a change of A0, -1/c chi dot. And then you see that these terms actually combine together in a total derivative, 1/c integral dx di EI chi dot. And so integrating this total derivative and assuming that fields vanish at infinity, at a special infinity, we obtain that dl, delta L, variation of the Lagrangian is actually 0. So indeed, we see that our phase space Lagrangian maintains this symmetry, well, as it should. So gauge symmetry is there. If you would like to write down equations of motion for the gauge potential itself, not for electric and magnetic field, then the use of Hamiltonian is not enough. So the correct equations, you need also to take into account the Lagrangian, the term with the Lagrangian multiplier. So dAI over dt will be the Poisson bracket of the Hamiltonian, this bold Hamiltonian, with a bold Hamiltonian, but I also have to take into account this term with a zero and the Gauss law. Like this, with AI. And so then you need to also to use the Poisson bracket of EI with AI and AI with H. And this will produce for you the correct expression for AI dot, which we have already seen by deriving the canonical momentum. Yeah, so then exactly you will reproduce the dot. Okay. Now,
excuse me.
Yeah.
Can you explain again this? Why you have subtracted Hamiltonian?
It's just a part. It's just a part. So what is standing there is just a part of the Lagrangian. So what I'm saying is that I need to take these both terms to account for equations of motion for our field AI. So if I want to write down equations of motion for AI, then I need to take into account this term as well. Now, if you will be deriving equations of motion for H and E, as we did here, adding this term will produce no effect because this term will commute with H and E. That's why I allowed myself to omit it, because it doesn't contribute. But it does contribute if you consider the equation of motion for AI. Okay? So in a way, this is a part of the gauge fixed Lagrangian. You see, it appears in the rest. It's what we call rest. And we know that there is a symplectic structure. There is what we would like to call the Hamiltonian for electric and magnetic field. But there is also this extra term, which we call constraint. This constraint does not contribute to equations of motion for E and H, and therefore I'm using only the Hamiltonian to write Hamilton's equations for E and H. But if I want to reproduce correct equations of motion for AI, then I also have to take into account the presence of this constraint term given constraint. Okay, that's the result of direct calculation. That's what you see from direct calculation, that you need to take into account, otherwise you don't reproduce correct equations of motion for AI.
Okay.
Now, the fact that you have this gauge symmetry around, symmetry which does not change your action or your Lagrangian, as we see, means that there are unphysical degrees of freedom, that your action contains too many degrees of freedom. So, in other words, description of our electromagnetic field by means of electromagnetic potential has a certain redundancy. This redundancy is clear because we know that physical observables are only electric and magnetic fields. In other words, components of electromagnetic tensor. But we build up electromagnetic tensor via electromagnetic potential by the formula F mu nu is d mu a nu minus d nu a mu. And then we clearly see that if we change the potential by adding up the gradient of any function chi, function which is a function of a space-time point, and it's arbitrary, then electromagnetic potential do not see this change at all. So in other words, our physical observables will not be changed at all. And so this means that electromagnetic potential, we are changing it in this way, but our observables do not change. We have the one and the same physical state. So this means that components of a mu which we have introduced are too many. There is a symmetry around which do not change those quantities which we can measure in experiment. So this electromagnetic potential allows us to nicely solve Maxwell equations. In particular, with this potential, we automatically solve the first pair of Maxwell equations, but we have to pay a price for it. The price is an introduction of unphysical degrees of freedom, and as a result, the gauge invariance of our action with respect to these local transformations depending on an arbitrary function. So this means that we have to somehow understand how to get rid of these unphysical degrees of freedom. Yes, question?
Yes, so, so shouldn't the electromagnetic potential be also is observable?
Electromagnetic potential, a mu, is not observable.
No, A0.
A mu.
No,
No.
A0, zeroth component. A0.
You should be careful here. When you say A0, everything here depends now on what we would like to do with our gauge freedom, right? So one way to do is to impose the gauge. So as I already probably told you, that the situation is as follows. So you have all possible gauge configurations of a mu. So various potentials as functions on space-time. Now, imagine that all these potentials represent a space. I write it as a manifold, but imagine that, yes, that this is a space of all possible a mu's. Now, you start from one particular a mu. Well, this is a point in the space of all possible a mu's. And then the gauge transformations starting from this a mu make an orbit in this space. So this means that all points lying on this orbit, this is an orbit. So if this is a particular potential a mu has been chosen, then this is an orbit passing through a mu by adding up all possible gauge, all possible gradients of arbitrary function chi. It makes a gauge orbit through this a mu. Then you take another potential which is not on this orbit, and through it you can also draw another orbit and another orbit. Sorry, and another orbit. And another orbit. And so the space of all the potential, of all possible potential configurations now is foliated by these orbits. And so 2 points lying on the same orbit, they are leading to equivalent physics because for all points on the same orbit, E and H remain to be the same, and they are only observables. Now, this means that if you would like to describe if you would like to remove unphysical degrees of freedom, it's enough to pick up from each orbit just one representative. One representative is enough to describe physics. You don't need to consider all of them because they lead to equivalent description. And so the way to do it is to impose the gauge. So in other words, to impose extra condition on the field A mu such that from each orbit, you will pick up just one configuration. Just one configuration. And imposition of this extra condition on the potential, which allows you to pick up only one representative from each orbit, is called imposition of the gauge. But it's clear that you can impose the gauge in different ways. You can pick up different different conditions in order to pick up a unique representative from each orbit. So there is a certain freedom in imposition of the gauge. Moreover, the gauges can be complete and incomplete. Complete means that after you impose this gauge, there is no any more possibility to consider gauge transformations without destroying this gauge condition which you imposed. That is called complete gauge choice. But sometimes it's possible to impose the gauge in such a way that there will be still redundant gauge transformations left over, which do not destroy your gauge choice. So the idea is that, of course, all complete gauge choices, which are well defined, should lead to the one and the same physics. They can be different, but they should imply the one and the same physics. Okay, so this is an idea behind imposition of the gauge. And then once you added to the theory this subsidiary condition, which fixes the gauge, you can write down the gauge fixed form of the action. So you can go to the action back and try to implement this gauge fixing condition and therefore write what is called gauge fixed form of the action. Now, what are the gauges or popular gauges or important gauges which people are using? So one of them is a Coulomb gauge, which we already probably I already mentioned it. So Coulomb gauge. Coulomb gauge condition. Coulomb gauge, which consists in imposition of divergence of A. If you wish, I can write it as divergence of A is equal to 0. So condition on the potential. So this is a condition which imposes on potential. And now coming back to your question on A0 equals 0, we have seen that in this gauge, divergence of A is equal to 0, potential A0 is automatically 0. In this gauge, yes, A0 is 0 as a result of solving equations of motion for a field A. And as you understand, what happens here is that we started from the 4 potential, which has 4 components. Now, solving algebraic equations of motion for A0, which comes into equations without time derivative, we remove A0, and then we impose one more condition, divergence of A is equal to 0, which effectively removes another component of A mu. So altogether, we remove 2 components from A mu, and we are left with, as you wish, with electromagnetic wave, which has 2 degrees of freedom. And these 2 degrees of freedom are 2 possible polarizations, which light or electromagnetic wave, if you wish, can have. And that's why we say that electromagnetic field has 2 degrees of freedom, because in the radiation gauge, Coulomb gauge sometimes is called radiation gauge, because it describes electromagnetic wave. Electromagnetic waves, if you consider sources and radiation, then radiation is precisely creation of electromagnetic waves. And so we see that in this gauge, we clearly understand that our electromagnetic wave has 2 degrees of freedom. Once again, because we need to impose subsidiary condition, divergence of A is equal to 0, this Coulomb gauge, and we solve algebraically for electromagnetic field, which tells us that A0 is 0. Now, continuing a bit with Coulomb gauge, it means that the potential, since A0 is 0, we are left with AI. AI can be decomposed into transverse part and a longitudinal part. Longitudinal part is a part which is proportional to a gradient. So to a gradient of some function, let's call it psi. And the transverse part satisfies an equation that the gradient, the divergence of di transverse is equal to 0. So if you start from an arbitrary field AI, then you see that di AI is di AI transverse plus di AI longitudinal. And so transverse part by construction that it's transverse vanishes, and the whole divergence then becomes equal to the divergence of the longitudinal part. So in other words, you will get here di, which is Laplacian, three-dimensional Laplacian, acting on a function psi. So if you impose the Coulomb gauge, that means that you put it to 0 in the whole space, and as a result, in the whole space, Laplace equation has only trivial solution, psi is equal to 0 in the whole space. That is a unique answer of the Laplace equation. No boundaries in the full space with vanishing boundary conditions at infinity. Laplacian has only one solution, which is psi is equal to 0. So this means that indeed, from this point of view, we are killing longitudinal part of electromagnetic potential, and we are left only with the transverse part, which represents 2 degrees of freedom of electromagnetic wave, or in quantum theory, this will correspond to 2 physical degrees of freedom of a photon.
Would you please explain this last decomposition in a bit more detail? Why do we?
Yes, I will.
What is the physical meaning of a parallel and a perpendicular, and why do we impose the constraint on their values in 2 different forms?
This is, in fact, well, first of all, this decomposition is known in mathematics under the name Helmholtz decomposition. Any 3-dimensional vector can always be decomposed into transverse part and a longitudinal part. So this is what is in mathematics called Helmholtz decomposition. It describes in mathematical books how to construct it, but I will do it maybe in a pedestrian way, but I will do it in a moment. Now, characterization is simple. That is exactly what characterizes the longitudinal part and the transverse part. So transverse part is a part which enters the field AI, such that its divergence is equal to 0. Longitudinal path, it's a path which is
So it's
equal to the gradient of some function.
okay.
Yeah.
And then I understand the theorem you are talking about.
That's Helmholtz decomposition of a three-dimensional vector field. Now, I will clarify it a bit further how to construct this decomposition, what is exactly, how you can build up what is a transverse. Exactly, what is this? Just wait a minute. I would like to to finish with gauges. So one gauge we have discussed.
Sorry, the last question. Why? Why again the divergence of the transversal part is 0 independent?
It's a definition of what you call transversal, if you wish.
Oh, yes, okay.
Yeah. When you say transversal or transverse, that means that divergence is equal to 0 by definition.
Oh,
okay,
yes. Now the last line of reasoning is clear.
Okay. So there is another gauges. Yeah. So of course, you see. So what happens here is that imposition of the Coulomb gauge breaks Lorentz invariance. It is clear because the condition which you write in here, DIAI, is not symmetric with respect to space and time, because time do not present here. You see, indices are summing only indices involved in summation are spatial. There is no time direction. There is no D0, A0. So this gauge choice is the one which breaks Lorentz invariance. And this is, of course, in a way, disadvantage of this gauge. Although it gives you actual physical degrees of freedom, so it's a complete gauge choice, you remove gauge degrees of freedom completely. The disadvantage is that it breaks Lorentz invariance. Breaks Lorentz invariance. And breaking Lorentz invariance is kind of, you know, you have to a posteriori, even if you do this theory, quantize it, and so on, you have to prove that in this gauge fixed theory, Lorentz invariance is still there. So you are quantizing still with the preservation of important physical principle that independently on the Lorentz frame, you describe the one and the same physics. And so if you're breaking Lorentz invariance, then you cannot be completely sure that the results which you obtain do not depend on the Lorentz frame in which you are making your computations. So working in the Coulomb gauge at the end of the day should be supplemented with a separate investigation that the gauge that Lorentz invariance is still present in your theory, in your gauge fixed theory, which might be a complicated question, of course. Now, there are other gauges. For instance, there is a Hamiltonian gauge. Sometimes they are called it's called Hamiltonian gauge. And this gauge is A0 equals 0. It's called Hamiltonian because in this gauge, the equations of motion for all remaining fields are obtained just from the Hamiltonian H. So you say 0 is equal to 0, then you completely remove this extra term, which describes a constraint, which is a constraint term. However, this gauge is not complete. This gauge is not complete because you are still left with time-independent functions which preserve the gauge condition. Indeed, if we look at the gauge transformations here, and you say we put A0 equals to 0, and we see how A0 transforms. It transforms with a chi dot. So if the function chi does not depend on time, then its dot is equal to 0, but still the vector potential will undergo the change by the functions chi, which are time independent. So vector potential, you still can rotate by functions which do not depend on time. You can shift potential by functions, by gradients of functions which do not depend on time. So this gauge choice is not complete. There are redundant gauge transformations. And finally, there is a covariant gauge, which people also use. It's called Lorentz gauge. Lorentz gauge. And it's given by the following condition: d mu a mu is equal to 0. Yeah, first of all, let me say that Lorentz gauge, you see how I'm writing the name Lorentz. There is no T here because it's a different Lorentz. It's not the Hendrik Antoine Lorentz, but this is Danish physicist with also Lorentz, but it's written without T. It somehow happens that both Lorentz, yes, Lorentz from Holland and Lorentz from Denmark, they both were involved in developing electromagnetism. And this is Lorentz who invented this gauge. And even in many books, people confuse these names. So they attribute this gauge to Hendrik Antoine Lorentz, which is not the case. Now, d mu a mu is equal to 0. So this looks similar to the Coulomb gauge, but summation goes over all indices. And so this condition is a relativistic invariant condition. So it's invariant under Lorentz transformations, because indices, you see, they run in all the range, 0, 1, 2, 3, and they paired in a proper way. So this is a Lorentz invariant condition. However, this gauge choice is not complete. That's because if you, this is, first of all, this is admissible gauge choice, because if you have, say, some gauge potential, a mu tilde, which does not satisfy this condition, and then you add to it, let's write it with upper index, and you add to it gauge transformation, so you transform it, and then you require that d mu acting on this term gives you 0, then you get an equation d mu a mu tilde is equal to minus box operator. Box operator is d mu acting on chi. And this means that what you consider here is what is called Helmholtz equation, or inhomogeneous wave equation, like this. So this is a box operator, or wave operator acting on chi. And on the right-hand side, you have a source term for it. And this equation you can always solve with the method of Green's functions. So solution does exist, and so this means that this gauge is legitimate. It's possible to reach it. It's possible always to subject the potential a mu to the Lorentz gauge condition. I said that it's an incomplete gauge choice because if you have a mu which satisfies the gauge condition, so d mu a mu is equal to 0, And if you add up to it the gauge transformation, satisfaction, let's write maybe this upper index. So A mu plus D mu chi. And if you compute the divergence of it, since d mu A mu is equal to 0, then what you're left with is a condition d mu chi. In other words, box chi is equal to 0. So if your chi satisfy the wave equation, homogeneous wave equation, box chi is equal to 0, then such chi's can be always added to A mu without breaking the Lorentz gauge condition. And so wave equations do exist. These are just waves in four-dimensional space. And so adding them up to A mu does not break the Lorentz gauge. So this means that this is not a complete gauge choice.